In this video, I'll be working on the following setup. The setup consists of controlling the flow of water in the following tube, the tube that you see here, and manipulating the flow of the water by using the pneumatic control valve that you see on the left of the venturi tube. So the flow is measured with the venturi tube, which is the primary element, and it is measured with the differential pressure transmitter. This figure is figure 233 from your control manual. This is the electrical connection. It consists, so I have removed the recorder because I'm not using it. So what I have is the PLC, which is represented by the FIC, flow indicator controller. I have the pneumatic control valve and the flow indicator transmitter. So those are the three instruments that I have in my electrical diagram. This is how the setup looks like. So the pneumatic control valve is controlling the flow of the water in the tube that is connected to the column. I have the venturi tube, which is my primary element, and it is connected through the 3-valve manifold, which is connected to my differential pressure indicator. But in this, now it is measuring flow and not pressure. So what is happening is that it's converting pressure to flow. And the flow is measured in liters per minute. That's how I have set it up. And both of these instruments, the pneumatic control valve and the pressure flow indicator transmitter, are both connected to my PLC. In order to measure the flow, what I have done is, of course, I have first bleeded the differential pressure indicator, and I made sure that the tubes don't contain any water, and I have set the zero of the flow indicator transmitter. There were adjustments that I had to do here. So what I did is I closed both of these valves, the high and the low. This is my high input, this is my low input. I've closed both of these, and I've opened this valve, so the isolator valve, and I have set the zero for my flow indicator transmitter. And then I also had to set the maximum flow rate for my flow indicator transmitter, and the maximum is 40 liters per minute. Another thing to note is that the flow indicator transmitter, I have to make sure that the measurement here corresponds to the measurement that I have in my rotometer. Otherwise, there would be a problem. And that's what I have encountered in the beginning. My flow indicator transmitter was not providing me the same value that I see on my rotometer. So let's take a look now what it is reading right now. It is reading 30.51 liters per minute. If I take a look at the rotometer, it's a little bit less than 30. It's a little bit less than 30. So I'm not getting exactly the same value. Earlier I had it at a different value, and the volume was much closer. Oh, here I have 30 now, 30.5. So now it's a little bit closer to the reading on my rotometer. I noticed that the flow indicator transmitter is sensitive. When I zero it, it doesn't give exactly zero. So if I stop the pump, it doesn't give me exactly zero. And but when I zeroed it, I took my time and I have made sure that it is zero when both of these valves, the high and the low, are closed and the isolation valve is open. So remember, for the Venturi tube, this is the larger cross-section of the Venturi tube, and this is the smaller cross-section. The larger cross-section is where you will have the high pressure, and the smaller cross-section is the lower pressure. So what I'm going to do right now is I'm gonna use the PID technique, pneumatic control technique, to control the flow of water in my pipe. So my controlled variable is the flow, and my manipulated variable is my controlled variable is the flow rate, and I am also manipulating the flow rate with the valve. So of course the level of water in the column will vary based on the position of the valve. What I've also done is I've opened hand valve 4 and 5. They're completely open. So this is hand valve 5, and this is hand valve 4. They're completely open. The only difference between my setup, the only two differences, is that I don't have the didn't connect the recorder, and I didn't connect the solenoid valve. But it does not change anything, because whether I connect the solenoid valve or not, it will not change anything to the output flow rate. So now what I would like to do is start with the P control. So I have set the set point to 50%, and the process variable is currently at 76.38. The control valve is 26 point. It varies 0.19, 0.21. So now this is P control, and already we can see that there is an offset between the process variable and the set point. We can see that by looking at the numbers. It's approximately 16% offset. So 50%, meaning that the set point is currently at 20 liters per minute. So remember my maximum flow rate that I have set is 40 liters per minute. And now the reading that I'm getting is approximately it's a little bit over 30 liters per minute. So there is a difference of 10 liters per minute. So there's a difference of 10 liters per minute. And so we can see that there's an offset, but everything is stable. It's fairly stable. Everything is fairly stable. I don't have any instability. And we can see that when we look at the graphs. There are two graphs. That's why I say there are graphs. So you can see it's fairly stable. There is a little bit of fluctuation with the control valve, but not so much. So what I'm going to do right now is I'm going to increase the so obviously this is automatic control. This is not manual control. I am not controlling the control valve, and I'm gonna just go and take a look at the P, TI, and TD. Actually, one more thing that I would like to talk about is my connection. So I have analog in 0 and analog out 0. So the analog in 0 is my input from my flow indicator transmitter, this one right here, and my analog out is my pneumatic control valve. Both are connected to my PLC inputs and outputs. So now what I would like to do is adjust the P. So I have only enabled the P, and I have this started with a small value 1, as prescribed in your manual. The TI and TD are disabled. So what I would like to do is start with adjusting the P control, and I will increase it. I'll increase it to 2, and now I will change the set point to 70%. I have to wait a little bit and see what I get. For the time being, I'll just go and take a look at what the manual says. So this is from figure 225 of the control manual, and there's the process response underdamped and oscillatory. So we're not there yet. So I don't see any fluctuations for the process. Looks fairly stable so far. That's the green line right above the blue. So again, we still have an offset, which is expected with P control. So I'm just gonna increase it again, double it, as prescribed in your manual, and see what I get from here. The set point has to be changed. Change it to 50, and see what the response that I get. Okay, again, it is fairly stable. The process variable is not changing too much. So this will allow me to again double the value of my P, of my gain. Double it to 8, see what I get this time. And change the set point. So there's an offset, small offset. You can see that approximately 3%, but not too much fluctuations. The process variable is fairly stable. So what I'm going to do, I'm going to increase it again. I'm going to double it again. And this time, again, I have to change the set point, see what the response is. It doesn't look like, if I take a look at my water here, you can see it's obvious, fluctuation is obvious, rotometer fluctuation is obvious, and I think it's pretty obvious here too. So what I will do, because of those fluctuations, your manual suggests that I should reduce this value now and put it in between the previous value and the current value, and that would be 12, because my previous value was 8, and 12 would be 4 units from 8 and 4 units from 16. So I will reduce this to 12. Now what I'm going to do, I'm going to come in with the TI. And I'll start with a large value. And I'll change the set point. So those fluctuations are not good. They're not good. We can see it here. The green is fluctuating. It's hovering over the blue, but it's fluctuating, and that has been caused by my P control. So what I'm going to do, I'm just going to return back. I'm going to return back here. I'm going to disable this. I'll go back to 8, and I'll change the set point to see if I get something more stable now. Still unstable. And change it again just to see what I get. So this is something that you have to do. You realize that when you put in the integral and you're getting oscillations, then you probably have to go back and adjust the P. So now it looks okay. It looks much stabler, and given that it is stable now, I will keep it at 8, and I will move on to the next value. So I'm just gonna change the set point here, 50. Actually, it looks like it's the integral itself that is affecting. So what I'm going to do, I'm going to go back, I'm going to disable, I'm going to go back, I'm going to put 12, which is the value that I had earlier, and I'm going to change this to 70 and see if I get something better. Start with a larger value here, with 80. So it's unstable. It doesn't look like it's going to stabilize. It's still fluctuating. So I'm going to reduce this to 8. Bring it back to 8. And I'm going to introduce this. And I'm going to reduce this to 50, the set point. See what I get. So this is PI control. So these are the values that I have right now. Lots of fluctuations. What I'm going to do right now is I'm going to reduce the integral. Reduce it to 99. Start with 99. We'll take a look at what your manual says. So bring the integral action by setting the integral time at a high value. Make a step change. Is the process response oscillatory? If it is, then set the integrand to halfway between the actual time and the previous time. So this is 99 is a fairly large value. It's 100. I can't take it to 100, but 99 is 1 unit away from 100. So I am getting an unstable response. So what I'm going to do is I'm going to go back to the P and change it again. I'll reduce it to 4 and see if that actually helps. now it looks stable. Take a look, there's an offset. It looks stable. So by reducing the P, it did help. What I'm gonna do right now is I'm gonna half the integral and see if I can get a better result, because now there's an offset, a small offset. See if I can close that gap. So I'm just gonna put it 50, change the set point. So you shouldn't be moving to the integral if the process is not stable. And that's why I didn't introduce the integral, because my process is unstable. So I have to, I want to follow the manual's recommendations and not any technique. So I didn't move forward because my integral, by introducing my integral, the process became unstable, and before moving to the integral, before introducing the integral time, I needed to make sure that the process is stable. So if you take a look now, I actually improved the offset. It's a very, very, very small offset now. And it's stable. Take a look here at the graph. You can see that stability. The green and the blue are overlapping. Here we can have a better idea of how far they are from each other. So your manual says that if the process is not underdamped and oscillatory, so again, decrease the integral time by a factor of 2, and that's what I'm going to be doing. So the integral time is 50, so reducing it by half is 25, and I'm going to reduce set point. Let's see what we get. So your integral time will make your process take more time to react. So the delay will be a little bit longer before you see the full effects of your automatic control. So there were small oscillations, but it looks like it has stabilized. There is an offset, but very small. So again, since there are no oscillations, I'm gonna decrease this again by half. I'll put 13 instead of 12.5 and see what I get. So it's very, very close. So the offset is very small and pretty stable. So since it's stable, I'm just gonna go and again reduce this by half. So I'll put it at 7. Okay, and change the set point again. Very quickly it reached the set point. With a very small offset. So since it's stable, I'm gonna attempt to reduce it again. Just gonna put 4 this time. Change the set point. I'll watch for any oscillations. If there are some oscillations, then I'm gonna increase the time for integral. So this activity, what we have here is I'm measuring the flow, and in another activity, which I will show in another video, what I will do is control the level of the water. I'll measure the level of the water and measure the flow, and I will use both of these instruments to transmit information to my controller, my PLC. And that will allow me to control the level of water based on the information of flow and the level. But for the time being, it's only level, it's only flow, that is, flow rate of water that I'm measuring in this activity. So it looks like it's pretty stable. It's pretty stable, and I'm not sure for the time being if I want to, because there were some instabilities before it got to being stable. So I'm not sure right now if I want to decrease again the integral. I can try it. Actually, I don't want to do that, because see these bumps right here? The green is above the blue. So there is some instability. Okay, so based on that, based on those instabilities, what I'm going to do is I'm going to increase the TI. So I decreased it from, it was 8, and I decreased it to 4. And so what I'm going to do is, actually it wasn't 8. It was, yes, it was 8. It was 8, and I decreased it to 4. So what I'm going to do right now, I'm gonna increase it to 6, and I'm going to leave it there. So now I'm going to bring in, so I'm going to reduce this to 1. And I'm going to bring in the integral. Change the set point. See what I get. what I'm going to do, it's not stabilizing. Doesn't look like it's stabilizing. Well, I'll wait a little bit. You can see that here. This is not good control. So what I'm going to do, I'm going to turn off the integral. I'm going to increase this back to 13. And I'm going to change this set point. And this is what you want to do. If things become unstable, then you're going to have to go back, make corrections to either the proportional or integral. This is not specified. Like what I'm doing right now is not specified in the manual how to go back. But this is simply what I have decided to do. Turn off whatever you've introduced, go back, and follow the manual's prescription. So now it's very, very stable. It's very stable with 13. And I'm going to reduce it. Very stable, so I'm going to reduce it to 7. 7, that is. Change it again. Change the set point. This looks much better. So this, so far it looks pretty stable. There is a small offset. So I'm not gonna reduce this again, because when I reduced it last time, that's when I saw, when I introduced the integral, the derivative that is, that's when things started to become unstable. So I'll give it another try. I'll change the set point and see what I get. See what your book says. So right now it looks fairly stable with some fluctuations, some oscillations. Very small offset. So what I'm going to do, I'm going to test it. I'm going to change the set point, put it at 20. I don't want the tank to empty. The tank looks like it's going down and down and down. So I'm going to actually just increase it to 40. Because I don't want the tank to empty, because if I intend on controlling the level, then the tank shouldn't be empty. So you can see here, these are my values for the gain, the integral, and the derivative. I don't think I'm going to go beyond 1 because the derivative is going to, if I make it larger, and when there are changes in the process, it will make my process less stable, and it will take more time for my process to reach the set point. So I don't think I'm going to go beyond 1. I think I'm going to leave it at 1. So let's take a look at the set point and the process very close. There's a small offset, but still very close. I'm going to change it again. I'm going to change the, going to make it 85. So this is what you want to do once you have your values for P, I, and D. Then you want to test. You want to test those values to see if they're actually working. So different values of set point may give you different responses. So you may not the response may be better for certain set points than for others. So you notice when I put a small set point value, my level of water was going down. It was the level almost emptied. And so these values will depend on your setup. It will depend on many things in your setup and your set point. Your set point for optimal results will not be for any set point. It will be for a certain range of values for the set point. So now I do have an offset. So when I have 85%, I have an offset. And so if you want to correct that offset, so 80%, 85 is 32 point, well no, it's not 32. 85% of 40 liters per minute, 40 liters per minute is larger than 32. But you see now I have an offset for this value, for when the set point is 85. So if I increase it, it should be the same thing. So 95%. So I expect again a set point, an offset. The offset is evident by the difference between the blue and the green columns, and we can see it here. So I have an offset for this set point, but if I reduce the set point, I'm going to get different results. So it doesn't look like it's going to get near. I don't know how much time it will take before it gets near. So I'm going to reduce this value and bring it to 45. I hope it's going to stabilize. So these are the values that I have. So this is not working very well. I'm going to disable again the integral. Change the set point, make it 45, make it 40. See what I get. It looks now stable. So what I'm going to do, I'm going to start with a small value here. Start with, let's say, 0.2, 0.1. And I'll introduce it, because now it looks stable. I'll introduce it and see by making a set point change if I get something better. It's pretty stable now, so I'm going to keep it there. I'm going to go to 80%. And you see it's getting closer and closer and closer. The green is getting closer to the blue. The blue is the set point, the green is the process variable, and it reached it right there. And you can see that here. So this looks like a much better value, 0.1. So I'm going to make another test. I'm going to take it to, say, 90. I don't know how well this works for 90. Earlier it didn't work very well. So it didn't reach it. And it doesn't look like it's going to reach it. So of course, this setup has limits. This control, this control has its limits, and you can check what its limits are. So I'll just take it to 30%. See what I get. Pretty close. I'm getting pretty close to the set point. So this is working pretty well. I'm just going to make one more change because right now we can see they're overlapping. I'll make one more change. Take it to 66. looks pretty good. So I don't think I'm going to be changing. Given what my experience earlier, I'm not going to be changing the TD. Of course, you're free to tune, restart the entire thing, the entire control, and reconfigure your PTI TD. But for me, I'm not going to be changing the TD because it gave me instability earlier, and now I'm getting fairly good results. So I'm almost there at the set point, some fluctuations, but it's getting stabler and stabler. And the control valve is not working, is not fluctuating as much. So what I'm going to be doing right now is I'm going to note these values, and whenever I have to restart again, the process again, I can start with these values, or I can start all over again. That really depends, because if you do some changes, any changes, so for example, if you change the position of your valves, or the length of these tubes, that can change a lot of things in your process. So I am satisfied with these values, and this will be the end of this experiment.